quick look at functions. So what we know about functions is we know that there's some sort of relationship between x and y, and we know we have this vertical line test for a function, and it's only a function if the vertical line will cut the graph of the function at one point only. We say that for a function, every x value has only one y value, and that defines it as a function. So when we look at functions, there's also a little bit of a further classification we can make, and that is about even and odd functions. So most of our functions are actually neither. So this function here, it would be one that's neither even nor odd. However, some of them have these unique properties which make them even or odd functions. And they're useful for us in sketching the function, and later on when we're doing other work of our own functions, the fact whether they're even or odd is actually quite a useful thing for us. And so these functions have the special properties of these functions. So if you have a look at an even function, you notice that with the y-axis here, it's perfectly symmetrical about the y-axis. So that's one of the properties of an even function, which means that when we're drawing an even function, if I've drawn one half and I know it's even, I can quickly draw the other half. I can say what's going to be symmetrical. The other thing with an even function is if I take a value here, and if I take the same value over here, sorry, not the same, opposite sign, negative a, then these two values are going to be exactly the same. And that's obviously because it's symmetrical. And so the defining characteristic of an even function, algebraically, is that substitute any number in, and of course we can't substitute every number in, so we just use a pronumeral to represent every number. So we use a, function of a is going to equal function of negative a. In other words, function of 1 equals function of negative 1. Function value of negative 2 is equal to function value of 2 is the same as the function value of negative 2. So that's the defining features of an even function. The other functions are the odd functions. Now, odd functions have to have some sort of point symmetry around the origin. And what point symmetry means is that I just rotate it back onto itself. So I picked up this curve and I rotated 180 degrees, I'd end up with the same function. So they have this point symmetry about the origin. Point symmetry about the origin. So that's a visual, and again, how that's useful is if I know a function is odd, again, if I've drawn one half, I can draw the other half. I can just rotate about the origin and get what the other half looks like. Algebraically, here's a, here's negative a, function of a, function of negative a. You'll see that they're spaced the same, they're the same height up there. So in other words, function of negative a is going to be equal to negative function value of a. So when we sub them in this time, we won't get when we sub the values in this time, we'll get the same answer, but they'll just have different signs. One will be positive, one will be negative. And that's defining features of an odd function. Alright, so it'd be useful to look at some examples of what sort of questions you might be asked. So the first one is to show that this function x squared plus 3 is an even function. To do that, we have to do it algebraically. So we have to go back, and what we're required to show is that function of a is equal to function of negative a. So what we'll do is I'll take a and I'll substitute that. We know from function notation, function of a means that I'm replacing my x with an a. So over here I'm getting a squared plus 3. Function of negative a again means replacing x, but this time with negative a. So instead of x squared, I'm getting negative a squared plus 3. Notice I've put the brackets around here because it's not just the a but the negative that's squared as well. So when I look at this one, I say, well, negative a squared, anytime I square a negative, I always end up with a positive answer. So I end up with just positive a squared plus 3. Now if I have a look at what I've got here, it's exactly what I had up here. So that's simply equal to function of a. So therefore, if function of negative a and function of a are the same, I can definitely say, therefore, it's an even function. Second example over here, determining if a function is odd or even, or sometimes they'll say determine if the function is odd, even, or neither. You start off exactly the same way. We want to do it algebraically. We want to substitute in this pronumeral in here. And so again, I'm going to start off with what function of a is equal to. This time I don't know what I have to prove. I have to say if it's odd or even. So I'm going to say function of a, wherever there's x, I put in a cubed minus a. Nothing further to do with that one, so I'll go function of negative a. I'll go that's negative a, and again, put in brackets and cube the whole lot of it, the negative as well, minus negative a. So wherever there was an x, I put a negative a into the function. Now, when I cube a negative number, my answer is always negative, so I get negative a cubed. And these two adjacent negative signs make that plus a. So far I've got a cubed minus a, I have negative a cubed plus a. So I can see they're not exactly the same. Straight away I can rule out the fact that it can't be an even function. I just need to check to make sure they definitely are an odd function. So I can look at this one down here and say, well, it's really close to this, but the signs are back to front. Now when the signs are back to front, I can take out a common factor of negative 1. If I take negative 1 out of this, I get negative a divided by negative 1 gives me positive a cubed. Positive a divided by negative 1, negative a. So I can see here my function of negative a is negative a cubed minus a. A cubed minus a, that's a function of a. So it's negative function of a. So therefore, odd. Here's another example of a functions question I like to do, and it kind of gives me an idea if students understand this concept fully. So sketch the graph of y equals x squared minus 2x for x greater than or equal to 0. So if I'm going to sketch that graph, I'm not going to plug in values. It only says for x greater than or equal to 0, so I don't have to draw the whole graph. I have to just draw the section where x is above 0. So I just draw on the axis this section along here. So what I do if I'm sketching this, I want to get some key points, the x and y intercepts. So for those intercepts, I know that for the y-intercept, I'd sub in x equals 0. So if I sub x equals 0, I've got y equals x squared minus 2x. Just by inspecting that, I can see that if I put x equals 0 in there, that's going to give me y equals 0. So straight away I know it passes through that point there. X equals 0, y equals 0. I'd get the x intercepts, and for the x intercepts I'd say y equals 0. So if I make y equals 0, 0 equals x squared minus 2x. A little quadratic equation equal to 0, first step, we try and factorise that. Common fact here is x outside of x minus 2. I've got two things multiplying to equal 0. At least one of them must be 0. So either x is equal to 0, knew that one already, or x minus 2 is equal to 0. In this case, this one would tell me that x equals 2. So now I've got two intercepts, 0 and 2. So I'll say 2 up here on the graph, 0, and I'll mark that one as 2. I know a little bit about graphs already. I know x squared graphs are parabolas. So I know that this is a parabola, this is a positive x squared. Positives are smiling, so it's going up like that. It's what we call concave up. So from 0, it started at 0, it's going to come down, it's going to come back up, and it's going to go like that. And that's a bit of a rough sketch with no real details on it. Now, the next part, if this graph is part of an odd function, sketch the remaining portion of the graph. So what it's saying is that if what I've sketched so far forms part of an odd function, sketch what the other half of the graph would look like. I know this graph's going to continue up here. What's going to happen down here? What we just said about odd functions was that they have this point symmetry about the origin. So what I'd be looking to do is I'd look to take this graph and rotate it about the origin. If I rotate this graph about the origin, I'm going to get the other section. It's going to come up like this to about the same height. It's going to come down. This cut through 2. Over here it's going to cut through -2. And it's going to continue on mirroring this as a rotation symmetry. So I'm going to get this happening for the remaining portion of the graph. I hope that's clear. Work. Stop button.